Welcome back to topic 33 for Algebra 1, arithmetic sequences. Now with arithmetic sequences, first we have to define what the heck is a sequence. A sequence is an ordered list of numbers. It can either be random or it can have a specific pattern to it. Now with arithmetic sequences, we're going to focus on the list of numbers that deal with a pattern. So specifically with an arithmetic sequence, it adds the same amount every single time in order to get to the next term. Now in order to summarize an arithmetic sequence or a list of numbers, we can write it in an explicit formula. There are two different ways that you might see this. Oftentimes, the textbook way represents it by the formula a sub n equals a sub 1 plus the quantity n minus 1 times d. Now, you might be thinking, what? It's okay. We're going to define what each of these variables means. So specifically, if we have this a sub n, this represents the term you want. And what I mean by this is the term in your list of numbers. So say I want to figure out, okay, what number is in the 7th spot? What is a sub 7? A sub 1 is the first term in your list. So what number starts this sequence? Now notice here how we have n minus 1. And this n is a big N. It's not a subscript like we saw at the beginning of this formula, but it's a big N. This stands for 1 less than the term number. And this is assuming that n is going to stand for our term number. Now D here stands for the common difference. Now the bullet below identifies what the common difference is and defines it. The common difference stands for the difference amount between terms. And since we know with arithmetic sequences we're adding this same value, then we're thinking about, okay, what number are we adding between every single term in order to get to the next term? Now notice how we said adds. So we can add a positive number, but we can also add a negative number. With arithmetic sequences, we never refer to this as subtracting, always either adding a positive or adding a negative. So that was one formula that we can use to represent the explicit formula for an arithmetic sequence. Another formula could be, you might see it in the equation y equals mx plus b. And I know what you're thinking. Wait, I've seen this before. Yes, this is the equation of a line. Specifically, this is in slope-intercept form. We have our slope, which is our m, and then we have our y-intercept, which is our b. And this shows that an arithmetic sequence can be represented by a line. They can be summarized in a formulaic approach, but it can also be represented by a line, or arithmetic sequences are linear. Okay, let's go into our first example so we can actually see this in action and kind of get a little bit more of a feel for it. So example number 1 says find the next 3 terms of the arithmetic sequence. So we have our first 4 terms listed here. And our first term is 0.02, or 2/100ths. So what we mentioned on the last slide was how we can represent values by a sub n, depending on what term we're dealing with. So here, we know that a sub 1 is going to equal 0.02. A sub 2, also known as the second term, is 1.08. A sub 3 is the third term, or 2.14. A sub 4 is 3.2, etc., etc. Now, in order to get to the next three terms, we want to identify, okay, what is term number 5 going to be, term number 6, and term number 7. So we want to figure out a sub 5, a sub 6, and a sub 7. In order to do this, though, we need to identify what the common difference is. Now, the common difference is what are we using to jump from one term to the next? What is this value? And when we're dealing with arithmetic sequences, this common difference is always going to be consistent. So we're not going to jump by 2 to get to the next term, and then the following term jump by 4. It's going to be consistent. So noticing here, we go from 0.02 to 1.08. Okay, well, we notice that our values are increasing, so we're going to be adding a positive number. But what specifically is this positive number? Well, we're adding 1, and then in order to get to 2/100ths to 8/100ths, we add 6/100ths, 1.06. Now, to make sure that this is consistent, we can test it out to going from the second term to the third. 1.08 plus 1.06 gives us 2.14, which is the third term, etc., etc. So what we have to do now is keep adding this value in order to get our fifth term, sixth term, and seventh term. So our fifth term is going to be 3.2 plus 1.06, which is 4.26. 4.26 plus 1.06 gives us 5.32. 5.32 plus 1.06 gives us 6.38. So those are our last three terms. I shouldn't say last, our next three terms. So I can fill them in here. 4.26, 5.32, 6.38. And we use that by identifying that our common difference, spelling, is 1.06. That's what we're adding every single time. Now with example 2, we're given this arithmetic sequence 3, -10, -23, -36. Notice here how I have it both in this list format, and then over on the right hand side, I also have it listed as a table with x and y. So we might see x and y, or we might see x and f of x. So just don't be surprised if you see that. We know that y and f of x are the same exact thing. So if we are starting with this arithmetic sequence, we know that this 3 is our first term. Now in order to get from one term to the next, what are we doing? We know our values are decreasing. So here, we're actually going to be adding a negative number. So in order to get from 3 to -10, how many jumps would we have to go on the number line? Or -10 to -23, or -23 to -36. Here, we are adding a -13. So our common difference is negative 13. Now for part A, I want us to write an equation for the nth term of the sequence. The nth term. Now this is to summarize, again, what our arithmetic sequence is. Example 1, I asked for the next 3 terms of the arithmetic sequence. But if we write an equation for the nth term of the sequence, this will identify if we want to find the 100th term later on, or the 10,000th term. It can help us by plugging in a value in for n. So again, I'm going to show it in 2 different ways, depending on which explicit formula you might be using. So first, let's start off with what's commonly seen in some textbooks. A sub n equals a sub 1 plus the quantity n minus 1 times d. And notice here, I put a little multiplication dot here to represent that, yes, we're doing multiplication. So, because we want to write an equation for the nth term of the sequence, with this equation on the left-hand side with this explicit formula, we want n to be in our equation. We want the variable n to be in our equation. We don't want to eliminate it. So we're going to start off with a sub n equals a sub 1. Now a sub 1 is the first term. And looking at our sequence, what number is the first term? 3. So we can plug 3 in for a sub 1. Then we have plus n minus 1, because again, we don't want to get rid of n's. We want to find the nth term, so we want to keep that n in our equation, times d. Now d is the common difference. What is our common difference? Our common difference is our negative 13. So it's really important that, again, you understand that this is multiplication, because I don't want this to look like we're just subtracting 13 after. We're really multiplying negative 13. So we can simplify this by applying my favorite property, which is the distributive property. Now this might look a little different than how you're used to. Usually we see that number before the quantity that we're distributing into, but this one it's just backwards. That's okay, because multiplication is commutative, so we can flip the order and it will still matter. And it will still give us the same answer in the end. So we have 3 plus a negative 13n, and negative 1 times negative 13 gives us positive 13. Now I can add my like terms. I have 3 and positive 13, and I get a sub n equals negative 13n plus 16. So that's my equation. Now if we want to use this with the y equals mx plus b, we're going to first identify what my slope is. So this is where I especially like to use the table. So we can identify slope, if you want a little throwback here, as change in y over change in x. So if you notice with our table method that we do here, what are we changing by on our y side? Well, here we're subtracting 13 every single time. So our change in y is minus 13. Now change in x, what are we jumping by on the x side? Here we're adding 1. So if we simplify it, our slope is negative 13, which actually happens to be what the common difference is. So here is where it will match up, but I just wanted to prove that it will be the same. So now we can write our template for our slope-intercept form of this explicit equation. So y equals negative 13x plus b. Now what we want to find here is b. We want to find the y-intercept. We know that our y-intercept is whenever x equals 0. So the y value here, or the 0th term, this will tell us our y-intercept. So how would we do this normally if we were just figuring out linear equations? Well, if we have our slope of negative 13, then what we do with our table is we would choose a pair. Of x and y. Now you could choose any pair. Think about this. If you're given a problem with a slope and a point on the line, can you write an equation to summarize that line? Yes, you can. We're doing the exact same thing here. Again, because arithmetic sequences are linear. So we can choose whatever value we want. I'm going to go with this one, just to change it up a bit. So, in for y, I have negative 23 equals negative 13 times, in for x, I have 3. Now this is telling me again that this is negative 23 is the third term in our sequence, which we can check over here. 1, 2, 3. Yep. And then plus b. Now I have one unknown in my one equation. I will be able to solve for it. So negative 23 equals negative 13 times 3 is negative 39 plus b. Add 39 to both sides. And b is positive 16. So if I want to rewrite my equation using my template that I had here, I have y equals negative 13x plus 16. And this is my linear equation. Notice how between the two formulas they match. Instead, we just have an n in the first one and an x in the second one. So looking at the one on the right-hand side, we can graph this. Now, before I move on, I have some people who usually ask me the question, well, does it matter which point you choose? No, it could be whatever pairing you want it to be. I just wanted to choose 3, negative 23, just for this example. Sometimes what students also ask me is, hey, I know I'm subtracting negative 13 on the y side in order to continue on with my sequence. Can I do the opposite and go backwards? So can I add 13 in order to get what the 0th term would be? Yes, you can. So if you are given the first number in your arithmetic sequence, you can also take your common difference and do the inverse of it to go backwards and find the 0th term. Remember, the 0th term would also be your y-intercept. I just wanted to show in this example to kind of build on what we've already learned in Algebra 1 by knowing what our slope is, having a point, and how we can plug that in to solve for our y-intercept. It's all connected. So what I'm going to do here is I'm going to graph this equation, y equals negative 13x plus 16 on Desmos, just so we have it handy for our next part of the example. So we have y equals negative 13x plus 16. Okay, here's our equation. Moving on to part B, what if I want to find a specific term in a sequence, but I don't want to have to keep subtracting 13, subtracting 13, subtracting 13. That can just get a little bit repetitive and annoying. And also, what if I was asked, what is the 300th term in the sequence? Thank you, next. Do not want to keep subtracting 13. I need something better to do with my life. So what we can do here is we can use the formula that we have in part A and plug it in. So I'm going to rewrite these formulas that we determined in part A. We had a sub n equals negative 13n plus 16. And in slope-intercept form, we had y equals negative 13x plus 16. So in this problem, we want to find the 15th term in the sequence. Now this 15 is identifying that, hey, whenever we see an n, we're going to plug a 15 in. Or whenever we see an x, we're going to plug a 15 in. So we have these two equations that we can build off of. So starting with the left-hand equation, this is saying that a sub 15, remember not a sub n anymore, we're substituting that 15 in for n, equals negative 13 times 15 plus 16. All we have to do now is just simplify. So a sub 15 equals negative 13 times 15 is negative 195. And then we want to add 16. Negative 195 plus 16 gives us negative 179. Now let's check with our slope-intercept form of the equation. Y equals negative 13 times 15 plus 16. We get y equals negative 195 plus 16. And y equals negative 179. So hey, it's the exact same thing. So without continually subtracting 13 every single time in order to get the 15th term, we can just plug it in. So the 15th term of the sequence is negative 179. So remember how I plugged in the slope-intercept form of the equation into Desmos beforehand? We're going to go back to that now. We can actually also use graphing in order to solve this problem. This equation, when x equals 15, this is an equation that we can also plug in and use the system to find that solution. So if we want to find the 15th term, I'm going to plug in x equals 15. Now we'll get a vertical line, remember, because x equals is a vertical line or an undefined slope. Let's look where these two lines intersect. They intersect when x equals 15, also known as the 15th term, and the 15th term so happens to be our y value here, negative 179. Now we could also do this again. Let's say I want to figure out what the, 29th term is. I could plug in x equals 29, get a value, and where my green line and my red line intersect, negative 361. So the 29th term of this arithmetic sequence would be negative 361. So we could also solve it with graphing, with tying everything that we learned beforehand with systems of equations. This is a system of equations. And that is it for topic 33 on arithmetic sequences. Thank you for watching.